So in this video, we're going to look at some of the basics of chemical reactions, what reactants are, what products are, and we're going to look at chemical formulae, and then we're going to look at how we can measure a reaction rate in a chemical reaction and why that's important. It is important. You can blow yourself up. Let's get learning. Welcome to these lessons in chemistry. What we're going to talk about today is chemical reactions and chemical reaction rate. Now, chemical reactions, we probably have learned this already, so we're just going to run through it very quickly. What happens is if one substance and another substance get together, there's a chance that they will have a chemical reaction between them, depending on how reactive they are. Now, you can increase the chances of them reacting with each other by, for example, heating them up. And we're going to talk about that in just a moment. But if we have a look at this slide, you'll see that I've represented the reactants. These are the things on the left-hand side of the chemical reaction, the things that I put into the reaction. So we write them on the left of a chemical equation. And they react to form. The arrow represents the term reacts to form. They react to form a new substance. And you can see here I've put a chemical bond between these two substances. So I start with substance A and substance B. There are reactants. And they produce a product called AB. Now, this product cannot, the chemical properties of this product cannot be predicted from the properties of the original substances. I'll give you an example. So an example would be that this substance A could be sodium metal, which is a reactive metal. If we put it into water, it will explode if the water is warm enough. And this is substance B. It could be chlorine gas. And chlorine gas is an incredibly toxic gas. It was used in the First World War to kill soldiers in trenches. It's heavier than air. It sinks into the trenches and killed all the soldiers until they figured out that wearing gas masks was the solution to the problem. But I take these two very, very reactive substances and react them together, and they form a new substance called sodium chloride. Now, sodium chloride is common table salt, and it is the stuff you sprinkle on your chips. And it's essential for life. So we take two things that are essentially quite dangerous to life, and we produce a completely new substance that is essential for life. And we can do chemical reactions various different ways. We can react. So when I take this substance here, it's now called a compound because I've taken two things and joined them together. I can take that compound and I can split it apart using various methods. I can react a compound with an element. So these would be elements up here, just the single substances. And I can get another compound and a different element, or I can release one of the elements from the compound and combine. So various different chemical reactions can be carried out, and this is a little diagram that describes those reactions. Let's move on. So when I'm describing a substance, either an element or a compound, remember, is a substance formed from more than one element. And I need to use a chemical formula to give that information precisely. I need to know how many atoms of any particular type of element are in the compound. So we use chemical symbols to indicate the proportion of each atom in that substance. And if you look at this diagram here, the aluminium, I have 2 atoms of aluminium. And then I've got 3 groups of SO4 ions around this aluminium. So the SO4 occurs 3 times. So the 2 here refers to the element that comes immediately before the 2. And because there's brackets here, the 3 represents the number of this group that we have in the substance. And then the 4 here is representing how many oxygen there are in this group. This is the sulfate group, sulfate ion. So these things here are chemical symbols. So each element has its chemical symbol. And they either have just a single capital letter or a capital letter and a lowercase letter that follows it to distinguish. Obviously, there's more chemical elements than there are letters in the alphabet, so we have to be a little bit careful there. Now, chemical equations are where we have to look at what happens to the substances during a chemical reaction. And if I use chemical symbols and formulae, I can represent exactly what happens in that chemical reaction. So here, for example, is hydrochloric acid reacting with calcium carbonate. It's a reaction we're going to see, and that forms calcium chloride, water, and carbon dioxide gas. Now, on the left, we put the reactants. On the right, we put the products. We use a number in front of this to balance it because we must have the same number and type of atoms on each side of the arrow. Remember, the arrow represents the direction of the reaction. And we can have a reversible reaction. I've drawn it in here because I couldn't find the symbol on my keyboard, but there is a way of finding it. I'll have to look at it sometime. And we also can use state symbols to represent what the appearance or the physical state, or the phase is the technical term for these substances, is in the reaction. So hydrochloric acid I add as a solution of hydrogen chloride in water. So that's an aqueous solution. That's what AQ. Calcium carbonate is a solid. It's marble chips. If you've got a marble floor in your house, you've got a floor made of calcium carbonate. Calcium chloride is a salt that dissolves in water, so it forms an aqueous solution because we've already got water in this reaction, right? So the salt is going to appear in the water. It's also going to produce more water, this reaction, which is a liquid. Remember, water is not aqueous, it's a liquid in itself, in its own right. And carbon dioxide is a gas. So this is a nice little reaction that shows us all of the stuff that's going on. So every reaction proceeds at a certain rate, and this is what we call the reaction rate in chemistry. And here we have some marble chips reacting with acid, and it forms that carbon dioxide gas. You can see that this reaction is occurring because you can see the bubbles of gas being given off. Quite often there are visual cues or auditory cues. An explosion, a loud bang, can be a cue that tells you that the chemical reaction has happened. But the only real sure way of knowing that a chemical reaction has happened is that a new substance is formed. For example, you can get a change in appearance of, say, water when it freezes to become ice, but it's not a chemical reaction because it's still water, even though it's in a different structural form. So we have to be a little bit careful. Phase changes can often look like chemical reactions if we're not careful. We're used to water, but many other things we may not be used to. Anyway, we observe the chemical reaction by the appearance of a product. So the gas forming here is an example of a product. The disappearance of reactants. The acid eventually will disappear. So if I take some pH paper, I can test this solution. And because there's plenty of marble chips here, eventually the solution will become neutral or a little bit basic because the marble chips might affect the pH of the water, but the acid will all have disappeared by the time the reaction stops. So many reactions are very slow. Rusting is a good example, rusting of iron. If you see a lump of iron in a field, you know, where somebody's left an old car or something, it's kind of an orange color, and that reaction is the steel, the metal, the iron in the car reacting and disappearing over time. Some other reactions can be incredibly fast. So explosions are fast. Sodium reacting with water, sodium metal reacting with water, which I talked about earlier, is a fast reaction. And we get reactions, chlorine gas reacting with the liquid in your lungs and the cells in your lungs is a fast reaction. Now, the end point of any reaction is reached when one of the substances is used up. And we have, quite often when we're looking at chemical reaction rate, we need to find the end point of a reaction. Now, there are various things that we can do to control reaction rate. And the reason we need to control reaction rate is because some reactions are dangerous. If we want to avoid explosions or avoid huge amounts of toxic gas being produced that are too much for us to contain, we need to be able to contain the reaction or slow it down and have it operating, have that reaction occurring at a speed that we can control. So it's a really, really important factor for industrial chemistry. How can you control the rate of a chemical reaction? Can you make it safe? There are other examples. So here, for example, we've got the catalytic converter in a car, and the catalytic converter in a car has to speed up the detoxification of the exhaust fumes of the car very quickly. So we're trying to get that reaction to happen faster. And there are four basic ways you can change the rate of reaction. The first one is increasing the temperature. The hotter things are, the faster they move and they'll collide. And collision theory, or a little bit of understanding of atoms colliding is an important concept in chemistry. So when atoms bang into each other, there's a chance they're going to react. The harder they bang into each other and the direction they are traveling at when they bang into each other, the faster, the more likely they are to react. Sometimes they just bounce off each other and don't react. So the faster they're moving and the particular angles they collide at increase the rate of chemical reaction. We can put more particles into the space. We increase the concentration or the pressure of a gas, for example. We can increase the concentration so we have more particles in the volume or in the space in a container, and that will increase the chemical reaction rate because there's more chance of particles banging into each other, and the more collisions that happen, the more chance there is of the chemical reaction proceeding faster. The more collisions that happen, the faster the chemical reaction will go. We can decrease the size of lumps of stuff. So for example, if I take marble chips and react them with acid, like we saw in that previous experiment, I can grind the marble down into dust and react that with the acid, and the reaction will happen much more quickly. The other thing you can do is take some iron filings and sprinkle them into a flame. That reaction will happen much more quickly. And you'll see the iron catching fire. You're not going to get iron to catch fire just by sticking it in a flame as a solid bar, but you take iron dust and sprinkle it on a flame, it'll immediately catch fire. So we've made the access of the particles, the atoms, to the iron atoms to oxygen much more, there's a much greater surface area for that reaction occurring. And we can add a catalyst, and a catalyst is a substance that you can put into a chemical reaction that will cause that reaction to speed up, and it will not be consumed by the chemical reaction. So your catalytic converter in your car, for example, down here, this catalytic converter, does not get used up as you drive along. You don't have to replace it until somebody pinches it from under your car, because quite often the catalyst that's used in these things is platinum or an expensive metal. And as a result, there's some criminals have a habit of getting under your car with a saw, cutting it off and running off with it, and it'll cost you £300 or £400 to replace it. So there you go. That's the reactions. Now, if I want to measure a reaction rate, what I have to do is I have to measure one thing that's involved in the reaction. So I can either measure a reactant that is disappearing, or I can measure a product that is forming. It doesn't matter which one I measure, because everything happens at a relative rate. So the reactant is disappearing at the same rate as the product is forming in a chemical reaction. So I can measure one of those things carefully over time, and that will give me a rate for the chemical reaction. So it could be the sensible thing to do in any of these chemical reactions is choose the easiest thing to measure. Don't choose, for example, in our reaction of acid and marble chips, don't measure the appearance of the calcium chloride because it's in solution. We can't see it, it's colorless. We can't see it, we can't get a measurement of exactly what concentration it is. The same thing applies to the hydrochloric acid. We can't see it disappearing. I mean, we could theoretically use a color system with an indicator and measure the color change that goes on, and that could be done, but it's hard and it requires specialist equipment. But the easiest thing to measure in that particular case is the carbon dioxide gas being formed, because it forms as a new substance that we can capture, and I can send it down a tube and into this thing here, which is a gas syringe that you can see in the diagram, and I can send a tube up to this gas syringe and send the carbon dioxide into the gas syringe, and it will gradually fill up with the gas as the reaction proceeds, and I can set a time for the amount of gas, and using that information I can calculate the rate of reaction. And I can change the rate of reaction for that particular reaction, calcium carbonate with hydrochloric acid, by changing the concentration of the acid. If I use a higher concentration of acid, the reaction will proceed faster. The syringe will fill up faster with gas. If I use powdered calcium carbonate instead of marble chips, the big solid lumps of calcium carbonate, that reaction will move faster. And it's actually quite important to tie the end of the gas syringe plunger onto the gas syringe with a bit of cord, because quite often if you haven't been expecting the rate of reaction, you can sometimes fire your gas syringe plunger across the room, which I'm not going to show you because they're expensive things to buy and I don't want to break one. All of mine have a piece of string tying them together so the reaction doesn't mess up. So anyway, there's an introduction to reaction rate. If you want to find out more about reaction rates, we're going to talk about measuring them and calculating the rate of reaction. And we're going to do that in our next video. So make sure you subscribe and like this video, and I'll see you in the next one. Thanks for watching.